The title of this talk is Optimal Subspace Estimation in Radar Signal Processing. I'm Kushalya Adhikari, Assistant Professor at the University of Rhode Island. The co-authors are Richard Baccaro and Vidab Al-Kinani, also from the University of Rhode Island. This work is supported by the Office of Naval Research. The goal in this work is direction and Doppler frequency estimation using a pulsed radar system. In this figure, we are showing an array of sensors. We assume that we have L sensors and we have a pulsed system. There are many space-time signal processing algorithms available to estimate direction and Doppler frequency, and our focus is on subspace-based algorithms. The question we're asking is how to improve the performance of subspace-based algorithms. We propose using optimal subspace estimates, OSE. And in this talk, I'm going to describe what OSE is and how to employ it. This figure shows a data queue in a radar system that has L sensors, M pulses, and N range bins. Along the vertical axis, we have the sensors. So this is the spatial direction. Along the horizontal axis, we have the pulses. So this is the slow time axis. And along this slanted axis, we have the range denoted by N. We can look at a space-time cut of this data cube for a fixed value of range N, let's say K, and we get a space-time snapshot for range K as shown in the right panel. And this panel also shows how to convert or how to map this space-time snapshot matrix into a data vector. We stack spatial samples corresponding to various pulses as indicated here. And this space-time vector is processed using space-time adaptive processing algorithms. We are first going to look at the sensor array. We have the sensor array with L sensors, and we are assuming that we have two targets of interest. Their spatial frequencies are FS1 and FS2. These are scaled versions of the angles that the reflections from the targets of interest make with the array axis. The spatial manifold vector for this uniform line array is as shown here. It's a function of the spatial frequency Fs, and it has a van der Waals structure. When there are two targets of interest, the array manifold matrix, it has dimension L by 2 as shown here, where Fs1 and Fs2 are the spatial frequencies of the two targets. This standard linear array is shift invariant. So what we mean by that is if we consider all but the last sensor in this array, then it has a different array manifold matrix. We denote that matrix by A top, and it is all but the last row of the original matrix A. Similarly, we can look at all but the first sensor in this array, and it has a different array manifold matrix. We represent that as A bottom. And this array is shift invariant because if we take this blue box of sensors and shift it, we can get the red box of sensors. It is manifest in array manifold matrix A as this. The column span of A top and the column span of A bottom are exactly equal. So the column span is equal to the signal subspace of the L-1 dimensional space, where L, again, is the number of sensors. And because of this shift invariant structure, A top and A bottom are related as shown here, where phi is a diagonal matrix. It's a function of the spatial frequencies Fs1 and Fs2. So if we have the array manifold matrix, we can compute the spatial frequencies precisely. But in practice, we don't have access to the array manifold matrix because it's a function of unknowns fs1 and fs2. So what we do have in practice is the data sampled by our sensors. So at first, we are going to look at the case when there is no noise, so everything is ideal. So in this noise-free case, we are denoting our data matrix by Y, and we perform its singular value decomposition, SVD. And the left singular vector matrix U can be partitioned as shown here into U1 and U2, where the number of columns in U1 is equal to the number of targets. And this U1 matrix also has the shift invariant structure. So if we look at the column span of U1 top and U1 bottom, they are also equal to the signal subspace of L-1 dimensional space. So the column spans of U1 top and U1 bottom, they are exactly equal as shown here. And as a result of that, U1 top and U1 bottom satisfy this equation from which we can compute the psi matrix, which is again related to the spatial frequencies fs1 and fs2. And we can precisely evaluate fs1 and fs2. But in reality, our data is going to have some noise, so we can't get U1 exactly. So let's see what happens when we have noise. When there is noise, we represent our data matrix and all other similar terms using the tilde symbol. And in this case also, we can perform the SVD of the data matrix. And we have this perturbed version of the singular vectors and singular values. And the dominant left singular vectors, if we take those and then try to evaluate the psi matrix, we can evaluate the psi matrix from which we can get an estimate of the spatial frequencies of the targets of interest. But they are not going to be accurate because unlike the noise-free left singular vectors, these singular vectors do not have the shift invariant structure. Their column span of U1 top and U1 bottom are not exactly equal as shown here. So what we've seen is that the array manifold matrix and in the noise-free case, the left singular vectors, they are accurate signal subspace bases. And in the noisy case, we have U1 tilde, that's an inaccurate signal subspace basis. But the good news is that we can use these inaccurate signal singular vectors and singular values. And based on that, we can actually get an estimate of the signal subspace basis, which we denote as X1. So X1 can be evaluated in terms of the available U1 and the singular values. And this estimate is going to be accurate up to the first order term in the noise matrix. And this noise matrix is, we don't have access to noise matrix either because in our data, signal and noise are going to be combined. But we can find the maximum likelihood estimate of this noise matrix. And once we find that, we can find the optimal subspace estimate, OSE, which we denote as X1. And we can use that in signal processing algorithms. So I explained the concept of OSE in terms of the sensor array because our spatial manifold vector has this van der Waals structure. But now if we look at our slow time axis, that is along the pulses are also, they also have manifold vector. And if we look at this manifold vector, it also has the same shift invariant structure because it also has, it's also a van der Waals vector. And as a result of that, the same idea can be implemented along the pulse dimension as well. So what we're going to do is we are going to look at the space-time matrix simultaneously. So if we have a space-time snapshot, then where we have the sensors along the vertical direction and the pulses along the horizontal direction, we are going to split this matrix into two submatrices. The top left shown by the red block, and the top right, shown by the green block. These two submatrices are related by this equation because of the shift invariant structure. So we get a set of constraints that need to be satisfied here. Similarly, we can look at the top left submatrix and the bottom left submatrix. These submatrices have to satisfy this equation because of the shift invariant structure. And one more, we can look at the top left submatrix and the bottom right submatrix shown by the purple block. And these submatrices have to satisfy this equation. So we get a set of constraints, and if we combine all those constraints and put them together as an equation, we get this matrix equation. And looks a bit complicated, but we can solve for this vector z using the min-norm method. And once we have the solution for this vector z, we can reshape it into a matrix form z, which we need to find the optimal subspace estimate x1. So we find x1 in this manner, and this is the signal subspace basis. We can also find the noise subspace basis in a similar way, and it can be used in subspace basis based algorithms. And in this work, we used music, multiple signal classification. So we considered different data sets, simulated data sets. In this case, there are many sources, and we are comparing the music output when we use eigenvectors or singular vectors directly versus using optimal subspace estimate. And in the top panel, so we have music output for eigenvectors. On the x-axis, we have Doppler. We have spatial frequency, and on the y-axis, we have Doppler frequency. And in the bottom panel is the music output when we use OSE. And as we can see, the resolution is much higher when we use OSE. The white lines, the grid, indicate the actual Doppler and spatial frequencies. So this is just one realization, one music output. We also looked at mean squared error plots. In the top plot, top panel, we fixed the number of snapshots to about 49, and we are varying the signal to noise ratio from -5 dB to 20 dB, and we are plotting the mean square error in dB scale. The purple line is for when we use singular vectors or eigenvectors directly, and the blue line is for OSE. And we can see that the error is much lower when we use OSE compared to singular vectors. In the bottom panel, we are fixing the SNR at 0 dB, and we are varying the number of snapshots up to 100. And in this case also, what we can see is that with OSE, we get lower error compared to singular vectors. So to sum up, spatial and temporal manifold vectors in space-time adaptive processing have shift invariant structures. And the shift invariant structures can be exploited in finding the optimal signal and noise subspace estimates. And if we use these optimal subspace estimates, then they significantly improve the accuracy of subspace-based space-time adaptive processing algorithms. Thank you.